So here we're going to talk to you about some work that also deals with AI and graphics, but with a focus of improving cities in the US and around the world. So first, a little bit of background about what are cities. So at first, cities were relatively simple places, maybe created by nomads. Then they became a little more sophisticated. They got built into mountainsides or mountain tops like Machu Picchu. And then, of course, nowadays we have much more intricate urban environments like Chicago, New York, Riyadh, or Singapore, with much more details and, of course, many more people. Now, if we look back at the way urban planning was done historically, the Spaniards, say, colonized South America in the 1500s, and they founded several cities, and they had a formula they used, a magic formula. The formula was, let's make the plaza. Next to the plaza, you put the palace, church, courthouse, prison, and give out the other blocks to the rich people. And there we go. That was urban planning. That's all that was done. And this worked. And in fact, we look at ancient plans or old plans of cities. This is how it was done. Doesn't work today, right? Things are a little more complicated. And one detail is, of course, the number of people. So you can see the number of people, which is most of us, when all of us live at the very, very end of this curve here, right? So there's a lot more people today than before, and this is a significant complicating factor. And these number of people bring significant issues like urban sprawl, traffic, pollution, flooding, and some of these events and extreme weather might actually be exasperated by the fact that the city is there. So maybe, people who study urban atmospheric sciences ask questions like, does the city actually increase the probability of there being lightning storms, tornadoes, flooding, and so forth? And I work with people who try to address these things. Another detail is that most people, as we've already heard of in the news, live in cities, but in fact, most people live in smaller cities, not in the big famous cities you've heard of. So here's a statistic. There's 19,000 incorporated urban places in the US, and 16,000 of those are quite small, right? 10,000 people or less. So most people live in small and medium cities, not in New York, Chicago, or LA. If you go to Europe, a very similar distribution can be seen. Most people live in the smaller cities of 50 to 100,000 people. So there's a problem here, one of missing data, where 80%, if we sum this up roughly, of people living in cities are not in the big metropolis, not in Chicago, New York, Beijing, Paris. They're in these smaller cities. And the unfortunate aspect is that the large metropolises, like New York and so forth, are data rich. There's lots of data about those large metropolises, but that's not where most of the people live. So here's some examples of the resulting, what I'm calling missing data phenomena. On the left, for instance, this is Planet Labs. So the whole world is captured by this constellation of satellites at some resolution. So you can see these images are of the whole planet Earth, but there's missing details. We can't see everything. The resolution is limiting. If we go to the next one, this is Worldview. This is the highest satellite resolution out there, but this doesn't capture the whole world regularly. In fact, like 1% of the world at most could be captured per day. So there is maybe medium details, but there is missing information. And still, if we go to ground level and look at some of this, we can see some missing details of buildings, facades, and so forth. Another category is, of course, aerial data and ground level data, which is perhaps very high detail, but that's definitely not full coverage. We don't have imagery that we capture regularly of everything from every direction, from the ground or from the planes. Then there's also crowdsourced data, metadata that human computing brings together, and that might be incomplete in some cases. So these are some examples of information where it would be great if we had this in more detail. So the missing link, I think, is an urban AI, an urban artificial intelligence. We want to teach the computer to automatically build or program 3D models of urban spaces. So what I mean by this, maybe we only have this input, this building, but yet we want to be able to produce everything about that building. And the way we think about this is using AI to generate a plausible version of this building that has all the details that we want, some program that generates it, like a ChatGPT, you can think of it, which was mentioned this morning, but it produces it from very limited and incomplete information. And this is, in fact, what we have been doing. So we generate statistically similar and plausible synthetic buildings and cities. We use whatever input information you can provide us, crowdsourced data, satellite, aerial, whatever the imagery is, and we're going to use the advantages of deep learning, of AI, and some other algorithms and optimizations to generate a likely completion of that data to produce what the city we think is, what the building is, what the neighborhood is, and all the details that we want. So in some sense, we're producing more than what we can see. That's kind of the objective. And it's what we have been doing for a while, since before AlexNet with many people, so I'm the one up here in front, but this work is a result of many collaborators and graduate students over the years, and I'm only going to be showing you a sample of results from the past few years, in fact, from the last 2 years mostly, some things that we've been doing with this urban AI. So this is one example where given some satellite and what's called land scan and height information. So land scan is an effort to spatially map out how many people are in every square kilometer on planet Earth. There's a land scan project, and there's a similar one in Europe and is being done in Switzerland. So we use the one from Chicago. And so this, together with satellite information, we can infer a building model. So this here is on the right is a view of Chicago and a zoom in, but this is all synthetic. It's all hypothetical, created from 1 meter satellite global height information and global population information. We generate a likely synthetic version of Chicago that we then use for a variety of things. Here's a video, which maybe I don't know if I can play this. What happens? No? All right. So this is a video that flies over a few cities to show you the 3D model that was synthesized. Oh, okay, there it is. This is a video of Chicago and a few other cities showing you kind of a demonstration of some of the outputs produced. These are hypothetical cities, but that are statistically similar to the actual reality. So for instance, we use this to do weather simulations. So WRF, WRF is maybe the most commonly used regional weather forecasting system, and it requires information about cities they call the urban morphology, so it can create weather predictions precisely and so forth. Most of the weather predictions you see do not use urban information. They're very generic, very regional. This is very specific to what's happening in the actual city. So here we did some study using our synthetically generated city that's similar to reality, compared it to several other kind of controlled runs, and pretty much it comes out working equal or better than whatever is out there. So therefore, it's accurate enough to do local weather simulations at the urban scale, at the individual city block scale. So this is recent work, and we're excited about that. Here's another work. So this is one where we tackle the resolution limitation. So here we see some satellite image, and that's 3 meters per pixel, some resolution. We can't see all individual details. So kind of the current status quo, how this will be addressed, is doing things called super resolution, segmentation, and so forth. And those are the bottom 2 images you see here. It doesn't quite get you all the detail. The upper right is the actual ground truth, and we produce the upper left. So again, we do this because we know something about how cities work, about population. We have that very blurry input, and with this, we're able to generate the likely completion of what actually was there. And it's not perfect as compared to reality, but it's better than other approaches. Again, we're generating kind of in a ChatGPT style what the city is in that satellite image. And here are some comparisons to other approaches and so forth, and our results on the right, and it's 50% better than prior approaches. All this is generative AI results. This is the example, and here's another solution. It's the one I showed you towards the beginning, where from a single picture, we're able to infer the entire building. So the input is the single image on the left, and the output is a full 3D model on the right, which you can view from any direction, do whatever you want, right? And we infer this from the single image. Again, this is what we mean by trying to fill in the missing details with a generative AI solution. This is a very similar idea, but instead of doing from a single ground view image, this is from satellite imagery. So if we just use the satellite imagery, this is world view, the best satellite out there, and we map this down to individual buildings, this is what you see. You see buildings that are fuzzy. You see, because of occlusion, there are trees on top of buildings, and well, that's the result you get. So again, with our approach, where we're trying to generate what's likely there and kind of see more than you can see, we produce something like on the right automatically for any of these satellite images. We've done this for many images, many cities, and we even had a cloud tool up for a while where people upload their images and we download the model for them, or download to them the model. So this is again a result of another one of our projects. This is something which is was from before, and we're doing some work now where we're detecting actually roof geometries. So this was some work where the input was a top-level view of roofs, and roofs are surprisingly hard to capture the details of automatically. And why would you want to know about stuff about roofs? For solar cells, for insurance purposes, how many trees on top of roofs. We've talked with people about that, but they want to know information about roofs. So here we're trying to determine roof geometries from these single images. In this particular work, the left side is the input and the right side is the output, where what looks like a roof really is a geometrical model that was inferred from the left. So it looks the same, that was the objective, but it really is full geometry on the right and pixels on the left. And we're still working with other directions in this today. Here's another solution. This is for trees. This is an exciting one we're still working on. So I could ask you, where are the trees here? Or how many trees are there in these images? Anybody have an answer? Plenty, yes. That's about right. And so here is actually where the trees are in this case. And this is another work which we're actively working on, where in fact the input is not exactly the image on the left, but it's 12 months of images like the left, so 12 images, one per month, so 1 year, 12 months of images. And from this stack of images, and again, deep learning, optimization, a bunch of stuff, we produce the right, which is an inference of where the trees are on the left, individual tree locations. And so we have these 12 months, go through some process of segmentation, then we have a generative phase using GANs, so generative adversarial networks, and we produce these tree locations. And we did some analysis and we did some scaling. So now we've in fact scaled this to all of the US, to all cities that have about 100,000 people or more. That's about 330 cities in the US that yield us an individual localization of about 275 million trees and over 8,000 acres. We did some evaluation of the performance. So it's pretty hard to get actual ground truth data, but we obtained this together with some help from Google for 20 different regions across the US, ecoregions. And for each ecoregion, we picked 1 or 2 cities and some analysis, and it's 97% accurate. Anyway, this is an exciting way of generating individual trees, and then we're doing more with this. In a very similar way, we also ended generating layouts. So this is combating the issue of human computation, or metadata is not necessarily providing all the information about a city. So perhaps there are some building informations, layouts produced by a city that they store it somewhere, but it might be incomplete, like this picture on the left. So we have a mechanism here to generate the rest of the buildings. And this is quite exciting. Here what we're saying is that we only need to know a fraction of the building information in the city, and we can generate the building layouts and heights and geometries of all the buildings from only a small fraction. So the way we did this is we looked at these same 330 cities. We picked, and we, through a bunch of working and together with RCAC using 100 GPUs and analysis and stuff, we came up with a methodology where, given only a small fragment of this information, we can generate the building footprints and envelopes and heights of cities, of buildings throughout the US, of 75 million buildings, from only 1%. So in some sense, this neural network has learned how to generate buildings that exist in the US. And this is pretty cool. And in fact, in the poster session during lunch, this one and the previous one were actually shown. I wasn't able to go, but maybe you were. This is some example outputs. So these are cities that are generated by this generator, some layouts, and if we compare this to reality, right? So this is left-right comparisons, real data and our data, and we have much more statistics. It's all very similar. So really the AI engine is able to learn how to generate cities quite well from only a small amount of information. And more like that. So one experiment we did, for instance, with this type of result is knowing only a fraction of the information of a city, we can generate the rest, and then we can perform these same weather simulations we talked about previously at the urban scale, so at the individual city block scale. So from this urban data, we infer information needed to run an urban weather simulation. For instance, plan area ratio, building surface to plan area ratio, area weighted building height, and things that are needed to be able to perform an urban weather simulation. We generate these, we run weather simulations, and basically all the top graphs and the bottom graphs look the same, which means that we're able to pretty much generate the same as if we actually had full knowledge of the city. Now in the case of Chicago, it's a very well-studied city. We do have full knowledge, but we did this for 25 other cities, so 26 in total, where we don't necessarily have all the information and get similar quality results. So that's where the exciting part is. And finally, another solution is archaeology. So ancient sites are in fact also cities. And we have incomplete information. In this case, not because we didn't go and capture or it's too much work, because it's gone, right? I mean, the rest of the city disappeared because of many reasons over the millennium or decade or millennium in this case. So this is the first work where, given just these fragments of the footprints of buildings, we want to infer the rest of the footprint of the building in equal or better way than humans can do, and this is what we're able to do here. Another one that we're currently studying is in Peru, in South America. There is some class of ruins where they believe there's like 30,000 mini cities around, and they've actually taken photographs by satellite of 7,000 of them, and they've studied 2 because these are hard to get to and it's expensive and so forth. So there is 30,000 such cities, 7,000 they have some detailed imagery about, 2 of them are studied, right? So wouldn't it be great if we can use this tool to complete those 7 or 30,000 cities and learn more about the history of that particular case in South America. We've also working, this is information from Turkey. This is from an island in Turkey. Same thing here. And we're also working with Greece, where there are some other still cities which are to be discovered, and there's only fragments of information. And we ask the same question, how can we complete it from only a partial amount of information? Now, this is the Greece site, actually. And this is, in some sense, what we want to do is, from the left, produce the right, right? That's the goal. This doesn't exist yet. And we don't want to completely do the Hollywood solution, just make up something, which, of course, we can do. We want to have some kind of a numerical, quantitative foundation to produce this, right? Some way that we can say the left really produced, the right really is the potential completion of the left. This was produced, in fact, by an archaeologist who's, 10 years, after 10 years of study of this one site, came up with the following conjecture of what this building probably was 800 years ago, right? But so that's what we want to try and accelerate. Okay, so these things about urban AI, I don't have time to go into it, but we've used them in various applications. Cloud control, temperature mitigation, greening, flooding, and urban traffic, to name a few. We've generated buildings and cities and used them in this to try and improve the design and planning of cities going forward. So maybe in this work, turns out that the albedo and material of a city affects the local weather, not surprisingly. So how can we alter the geometry and materials of a city to produce a desired, more likely cloud pattern? That will be one study we worked on. Temperature mitigation, clearly, urban heat island, urban cities absorb heat, radiate at night. So how can we reduce the heat effect in a city? So by white roofs and parks is one way. We've studied in that. We've done big scale greening. So if we could play God and we could move parks around, how does moving parks around the city, this Indianapolis, affect the weather? So we've again enabled tools like this. Also flooding, there is active flooding tools where you put channels and walls and dikes to redirect water, but there's also a notion of passive flooding control. How do you design the city to be more resilient to flooding, or to be able to sustain a flooding event more, with less damage? So we correlated urban design parameters with the effect in flooding using simulators together with some collaborators in Belgium. We've also looked at traffic and CO, carbon monoxide production, and how we can alter the design of a city to reduce traffic as well as carbon monoxide production. Anyway, so I want to use the last few minutes to address a kind of a question I'm putting forth in my head is, why should we do any of this digital twinning? Why should we digitize any of this? Is this the right thing to do? So what is it and why should we? So Warren Weaver, some years ago, has a famous article called Science and kind of Complexity, and people have gone through different variations of this idea of sense, manage, analyze, and provide, and many different words that pretty much have the same idea, right? Smart cities and many collaborators. These all seem to kind of, generative AI, all seem to point to, let's, take the world, let's digitize it, let's think, and then let's compute an answer. Is this really the way we should be doing things? And now it's called digital twins. And this is a known triangle, right? There's city, there's people, there's environment, and these things interact. And people are saying we should make a digital twin. And this morning, they mentioned the NVIDIA Omniverse is an attempt to try and have a digital twin supported by NVIDIA of the reality. Destin-E is a European effort to do a very large-scale, world-scale digital twin. So let's go back and think about computing, right? So this is a definition of computing in Webster. Determine, calculate means of a computer. There's computability, right? Alan Turing defined this 50 so years ago, 70 years ago by now. Social computing is another computing word, also known as human computing. There's environmental computing. These are other computings, right? A tree is actually a computer, but a tree is a physical computer, right? The input is soil and water, maybe carbon dioxide, and the output is maybe oxygen and biomass. There's a building. A building is a computer. The input is perhaps energy, and the output is comfort and shade, perhaps, right? Are these sense, analyze, actuates? There's also computational finance. So I worked many years with Paul Waddell. He was one of the leaders in urban simulation, and he really thought that the growth of a city is dictated by the real estate market, by finances. So we have to understand that to understand why a city becomes what it does. That's really the driver. So that's even a different understanding of a city, right? It's not geometry, it's just money. Right? So that's another type of compute. So why make a digital twin? Does it make sense? Why not compute using trees and buildings? why replicate a tree? Why not let the tree be the computer? Let the building be the computer? What does that mean? Can we do this? So, here is some idea. If we, what's the goal, right? Maybe the goal is accuracy. So if we were to try and replicate soil tree environment in some digital world, digital twin, and go all the complication of doing this, maybe the accuracy won't be that high because we're trying to understand the complexity of reality and program it into a computer. The preparation time is going to be high because it's going to take us a long time to develop this model. Once we've done this, though, the analysis time is low, right? We press a button, we get a result, and we can do stuff. Another option is kind of the inverse of one, where let's just put sensors in the world around the trees and the soil. This will give us a high accuracy because it is the actual environment that we're actually measuring. And then the prep time is low because all we do is send some undergrads out there with some sensors and throw it out and give them pizza, right? So it's very low prep time. But the analysis time might be long. Say trees, takes a tree 30 years to grow, so you got to wait 30 years to get an answer, right? So that's not practical. But maybe we should be asking things along here, and if we're trying to do accuracy, quickness, cheapness, or any answer, right, there might be other ways that we can try and understand reality beyond making everything digital. This interplay between the digital reality and the physical reality, we need to explore in more detail. This might redefine the notion of asymptotic complexity. So in computer science, you've probably heard we talk about linear algorithms, n squared, n cubed algorithm, and this is great. But does this really matter in these things that we're talking about? Is that really, or do we want some new notion of asymptotic complexity, a new notion of efficiency? Should there be new performance, accuracy, and cost metrics? I don't know the answer to these questions, but these are things I'm asking after I've been working this for almost two decades. We're trying to make everything digital, right? Is that really the right approach? Or should we be integrating ourselves more with the environment rather than trying to make everything work in a computer? Anyway, more thoughts coming soon, but I want to throw that out there to see if I get any reactions. Thank you. So a lot of people funded this. It's great stuff. We're doing more things. Any questions, please see me. Or ask me now. Yes?
I'll bring the microphone up.
Oh.
I can speak up. I was very interested in your picture of when you're counting trees.
Yes.
And that led to a question I had. So you predicted the trees. If you sent your undergrad out there and had him count the trees, how many would be there predicted? How many would have been missed, and how many would not be there that had been predicted? So what are your false positives and false negatives?
Yeah. So we have looked at that for 20 cities and the main part of 20 cities, and we have actual numbers, and I can share them with you afterwards. But, so the error is 5 to 10%. 5 to 10, yeah, depends on some conditions, right? But the interesting thing is, but we can do this at scale. So the whole US. So now we're looking for some interesting analysis, like where there was a forest fire before and after, what do we get? Or a tornado before and after. And we've gotten so far some good initial examples of that, which we'll be reporting soon. So that's one objective.
Here's another question.
Yes.
And it's also about counting trees. Obviously,
okay.
this is the best part of your presentation. But I mean, trees are great, so we should take care of them.
Trees are important, yes.
I was fascinated by the fact that you said 273 million trees in the US.
In urban locations.
This was the clarification I wanted to find out, because otherwise it's less than 1 per person. It's really sad. And I remember Finland advertising itself as having 10 trees per person on Earth.
Oh, wow.
You should probably point that satellite over Finland and put your algorithm to work to see if they cheat there or not.
So we've been focusing on urban locations, and that's what our method can count now. Going to non-urban, we're touching that, but haven't finished that yet. So the number was for urban locations, where there's less trees than in the Amazon, right, which is a different beast.
Thank you. Any other questions? Great. Thank you very much, Dr. Aliaga.
Thank you.
Aliaga.